Regarding immobilization of enzymes. Enzymes are biocatalysts that catalyze biochemical reaction in an organism. The unique feature is their substrate specificity. They catalyze a biochemical reaction under optimum conditions of temperature and pH. They remain unaltered after the reaction is completed. They can be used again and again. However, there are limitations too. They have low stability and are highly sensitive to adverse conditions. Biotechnological methods of producing enzyme is expensive, requiring specific techniques and defined conditions. These limitations are overcome by immobilization techniques. An immobilized enzyme is an enzyme attached to an inert, insoluble material. It also lets enzyme to be held in place throughout the reaction, following which they are easily separated from the product and may be used again. It is an efficient process and is widely used in industries for enzyme catalyzed reactions. The term immobilized enzyme is used to denote enzymes is physically confined or localized in a defined region of a space with retention of their catalytic activity and which can be used repeatedly and continuously. There are different advantages of immobilization of an enzyme. With these techniques, the enzyme can be recovered easily from the product. The product is free from enzyme and there is no cost of purification of the enzyme again. Enzyme can be used repeatedly. The enzyme generally gets stabilized after adsorption. Besides, there are disadvantages too. Some enzymes become unstable. There is additional cost of immobilization. There may be loss in catalytic properties of some of the enzymes. By immobilizing an enzyme, it can be used for various applications such as in industry for the production of antibiotics, amino acids, drugs, in food industry for the production of jams and jellies, in biomedical applications, in diagnosis and drug delivery, in biofuel production, in wastewater management, and textile industry. The techniques used in case of immobilization of an enzyme is the requirement of a support or the matrix, which can be a natural polymer, a synthetic polymer, or an inorganic material. The characteristics of the matrix are of paramount importance in determining the performance of immobilized enzyme system. Ideal support properties include physical resistance to compression, hydrophobicity, inertness towards enzyme, ease of derivatization, its biocompatibility, resistance to microbial attack, and availability at a low cost. Depending on the morphology, the support can be porous or not. Porous support material, for example, is silica, and the non-porous material can be glass. Based on their chemical composition, the enzyme can be an inorganic material or an organic material. The organic support can further be divided into natural polymers and synthetic polymers. Alginate are polymers of N-acetyl glucouronic acid having hydroxyl group which can be derivatized easily. Chitosan is deacetylated chitin. Starch is linear polymer of glucose. Pectin is a heteropolysaccharide made of galactouronic acid, which is present in cell walls. Collagen is again a polymer of glucose. Gelatin is synthetic support. Other synthetic polymers are DEA cellulose, PVC, activated polyethylene glycol, glutyraldehyde activated nylon. On coming to inorganic material, inorganic materials serve as a very good support. The surface of most inorganic support is mainly composed of oxide and hydroxyl groups, such as silanol group in glass, which provide mild reactive surface for activation and protein binding. Zeolite are microporous crystalline solids with well-defined structures. Ceramics, Cellite is highly porous diatomaceous material. Silica is oxide of silicon. Glass is highly viscous liquid. Activated charcoal, and charcoal is an allotrope of carbon, which has excellent adsorption capacity. On to the method of enzyme immobilization. The methods can be reversible or irreversible addition of enzyme to the support. While coming towards covering the reversible modes, it is the first one is adsorption. Immobilization of an enzyme by adsorption is easiest and fastest method. Adsorption is dependent on the experimental variables such as pH, nature of solvent, ionic strength, quantity of the enzyme and the adsorbent. Owing to the relatively weak binding forces between protein and the adsorbent, enzyme can be immobilized by simply mixing the enzyme with a matrix. Adsorption process is based on weak forces such as van der Waals forces, ionic and hydrogen bonds, hydrophobic interactions, and so on. Adsorbed enzyme can be protected from agglomeration, proteolysis, and interaction with hydrophobic interfaces. The adsorption through physical method generally involves multi-point protein adsorption between a single protein molecule and a number of binding sites on the immobilized surface. The main disadvantage of this method is that the enzyme is easily dissolved by factors such as pH, temperature fluctuation, changes in substrate and ionic concentration. But there are advantages also. It is easy to carry out, no reagent are required, minimum activation steps are involved, and it's comparatively cheap. In case of disulfide bonding, which is again a reversible method, the reactivity of thiol group can be modulated by changing the pH. Activity yield of this method involving disulfide bond is usually high. Dealing with the irreversible methods are covalent coupling. In covalent association, the enzyme associates with the support owing to the side chain amino acids such as arginine. In case of arginine, aspartic acid, histidine. There is high degree of reactivity based on different functional groups like imidazole, phenolic, hydroxyl, etc. The covalent groups in covalent coupling is most frequently an approach of immobilization in which covalent bonds are formed between amino acid of the enzyme and the matrix. Hydrophilic amino acids, which are likely to be present on the protein surface, can be exploited for this purpose. For example, amino group of lysine, cysteine, binds via SH, tyrosine, histidine, aspartic acid, and glutamic acid take part in bond formation. A number of chemical reagents and protocols are available for covalently linking an enzyme to the matrix. In covalent coupling, the enzyme can be directly attached to the matrix through covalent linkages. Covalent linkages are strong and stable, and the support material of the enzyme includes polyacrylamide, porous glass, agarose, porous silica. Covalent method of immobilization is mainly used when a reaction proceeds without requiring the enzyme in the product. The covalent binding of the enzyme with the support involves two major steps. The activation of the support material by addition of the reactive compound, and the second one is modification of the polymer backbone to activate the matrix. The activation step produces the electrophilic group on the support material so that the support material couples with the strong nucleophiles on the protein. Covalent bonding is normally formed between functional group on the support matrix and the enzyme surface that contains the amino acid residues. The amino acid residues involved in covalent binding are the sulfhydryl group of cysteine, hydroxyl group of serine and threonine. The attachment between the enzyme and the support material can be achieved either through direct linkage or through a spacer arm. The potentiality of using the spacer arm is that it provides greater degree of mobility to the enzyme. The enzyme shows higher activity when compared to the one directly attached to the matrix. The most commonly used method in covalent bonding are diazotization, formation of peptide bond, polyfunctional group reagents, by using bifunctional or multifunctional reagents, which form bonding between the amino group of the support and the amino group of the enzyme. In amidination, the matrix contains amido ester functional group, which can be used for immobilization of the enzyme. In thiol disulfide interchange reactions, the protein binding via thiol groups of both the carrier and the protein. Alkylation and arylation methods are also used. There are advantages as well as disadvantages of covalent binding. The linkage is strong. There is no leakage or desorption problem. The method is simple. There are various matrices or support material available. The disadvantages is the enzyme binding leads to conformational changes, as a result of which the activity of the enzyme is lost. Next method is the entrapment method. In entrapment and encapsulation, there is occlusion of an enzyme within a constrained structure, which is tight enough to release the enzyme while allowing the penetration of the substrate. However, because of diffusion limits, such methods are unsuitable for immobilization of enzyme. The advantage of entrapping the enzyme by enzyme immobilization is fast, cheap, and mild conditions are required in this reaction. The methods which are for entrapment are inclusion in form of gel, inclusion in form of fibers. Enzyme can be supported on the fiber matrix. inclusion in microcapsules, in which the enzyme is entrapped in microcapsules formed by monomer mixtures such as polyamine, calcium, alginate. The advantages and disadvantages of entrapment methods are, first of all, I'll be covering the advantages. It's fast, cheap, very mild conditions are needed, and there are less chances of conformational changes in the enzyme. The disadvantages: the enzyme can leak out of the matrix. The pore size can vary, which will again check into the leakage of the enzyme. There are chances of microbial attack. In cross-linking method, there is attachment of biocatalysts to each other by bi or multifunctional reagents or ligands. In this way, very high molecular weight, typically insoluble aggregates are formed. Cross-linking is a relatively simple process. It's not preferred because it does not use any support matrix. So it's they are usually in the form of gelatinous and not in form of film. It involves bond of the covalent type. Biocatalysts immobilized in this way frequently undergo changes in conformation with a resultant loss of activity. So these were some of the discussion concerned with immobility or immobilization of enzyme. So immobilization of enzyme has a wide range of applications in research field, industrial production, wastewater management, biomedical application, food industry, detergent industry, textile, and in production of biodiesel. So the industrial application of enzyme gets confined in a localized space by means of immobilization of enzymes.